Some stuff. Momentum balances. All right, today we are going to be talking about momentum balances. We talked about mass balances last time. Now we're going to talk about momentum. Okay, so why do we care about momentum when we're doing fluid mechanics? What does it have to do with fluids in particular? So F, a force, is equal to mass times acceleration. You know this. So it's equal to mass times change in velocity, change in time. A force is equal to a change in momentum per time. Okay? So that means that applying a force to something changes its momentum, and or changing the momentum, when something changes its momentum, it applies a force to something else. They're the same thing. That is why when you're driving in a car and you hit a wall, the wall exerts a force on your car, changing its momentum from whatever it was to zero. And also some of that force usually gets applied to you, and it's very bad. Okay? All right, so that means that a momentum balance relates to forces. Okay, so why does it take 3 firefighters to hold this hose? Anybody?
Because that water
Momentum.
some serious force.
Momentum, that is water. Who said momentum in a bright and pleasant voice?
That was me.
Hi, Mara.
Mara.
Okay.
Hi.
Momentum is the reason it takes 3 firefighters to hold this hose. Why, do you think?
I don't know. There's a lot of mass and a lot of velocity, so it makes sense that the momentum would be very large.
It is. Here's the thing. The important thing here is the change in the momentum, because the water is running along horizontally on the ground in this hose. And then what these firefighters are doing is redirecting the direction of the flow up so that it shoots out at the fire. Okay, so if they change the direction, then they're changing the velocity, which means they're changing the momentum, which means it takes a pretty big force, and then there's a pretty big reaction force pushing back on that hose, right? So those 3 firefighters, it takes all of their strength to hold that hose in that position, because that's what it takes to change the direction of the velocity there. And if they let go, it would smack down to the ground, right? Yes, Christian says that's why it snakes when it's just on the ground. That is exactly right. That is why a hose will snake around, because it'll push, the momentum will change that direction and it'll push the hose that way, and then back and forth like that. Okay. They're changing the direction of the flow. That takes force, and there will be a reaction force that they have to hold back against. Okay. Now, let's think about something we know and care a lot about at this point in this class, which is pipes. So water is flowing through a pipe. It goes through a pipe bend, which changes the direction. Okay, so does momentum change here? I already gave you the answer when I was just talking, but does momentum change here?
Yes.
Yes, right, because how do we know that momentum changes here?
Because the direction of flow changes, and that requires.
Yep, the direction of flow changes. So the momentum of that water going through that pipe bend changes as it goes through, because the direction of the flow changes. So let's think about that. So what direction is the force of the pipe on the water? And I'm going to call on somebody, so ready yourselves, be prepared. Let's see, Tiana. Hey, Tiana.
Hello.
Hi. So what direction do you think is the force that the pipe exerts on the water?
would you say that it's normal to the water since it's pressing in on the water?
Yes, that's good. That's a good thought. Yes, it's normal to the water. If you take the net force, and it's also there's viscous forces, friction forces in there too. If we took it all together and got the net force that is changing the direction of the water, what direction does that have to be? Like, what direction does the force have to point in order to change the water's direction like this?
Would you say it's going? Maybe I'm a bit confused.
Okay. All right. So that's good, because that means I want to make sure everyone knows what kind of forces I'm talking about. So let's say my phone is going in this direction, and it's moving and it's moving, and I stop it with my hand. Okay. I have changed the momentum of my phone because I have changed it from moving over here in this direction to the right, I guess. And so what direction is the force of my hand on the phone?
So it's going the opposite direction.
The opposite direction, right? And if, let's say, instead of stopping it, I made it bounce off like that, like I did it, okay? The force would still be in the opposite direction, right? It would just be bigger. So in order to change the direction of the flow of this water from going, let's say, to the right to going to the left, what direction is the force of the pipe on the water? It's basically like that. F of pipe on water. All right, does that make sense to you? That in order to change the direction of that flow, the pipe has to exert that force on the water.
I have a quick question about that. So this is the net force, right?
Yes, this is the net force of the pipe on the water.
So if we took a different point in that curve, would it still just be pointing towards the center of the circle?
So probably actually, well, it's just because it's going along right here and it starts to change in this direction, right? So probably if you zoomed in like that, yes, it would be going towards the center because it's making it spin around. But just overall, remember we were talking about control volumes? This is why we talk about control volumes. So implicitly what I'm saying is we're taking this, all of the water in here as the control volume. So all the water inside of there is the control volume, and I'm asking for the force of the pipe on the control volume, right? So you can just sort of, it has to do that in order to do it in the other direction. Okay, here's my next question. Let's say this is screwed onto some pipe system. The water is going through. As I say, you should be able to intuitively tell that the pipe is sort of pushing the water back that way in order to change its direction. Let's say that the pipe comes loose. This pipe bend comes loose and it flies off. What direction do you think it would fly off in?
Downward?
Sort of the downward? I would say it would fly off in the opposite direction, this way.
Oh, sorry. I thought you meant like it was like a going through a pipe, like long ways.
Because this is the force of the water on the pipe.
So if it was flowing, say like you have a straight pipe rather than a curved pipe, and it popped off, wouldn't the pipe go downward?
Probably, because there's no,
Because that's the only force that's acting on it is the
well, there's
downward
no
force.
change in momentum of, there's no net change of momentum of the water through the pipe. There's probably a slight net force on that pipe because of the change in the pressure. But that might do something a little bit, but it is that momentum that's doing this. Okay.
And I have a question with those arrows. So
Mhm.
is the reason that you drew that force of pipe on the water that way is because if you were to draw all of the little arrows along the way, all of the side to side would cancel out, and in the end, you're left with just the total, like the net force throughout that U bend of that direction.
That should be how it would if you wrote it all out. There's also, as I said, there's friction forces in there, but those should cancel, or those should be insignificant to what we're talking about.
Okay, but if you were to look at each point along the way, then there would be arrows kind of pointing towards the middle of that circle because the pipe walls have to kind of push that fluid as it makes the turn, right?
It should be. I don't want to say very strongly because I haven't thought that through in a while, but that is what makes sense. Is that it has to push like this. Because first it has to push it around like so. Okay. All right. That's the force of the pipe on the water, water on the pipe. So just like we used the Reynolds transport theorem and showed how that gave us a mass balance last time, we're gonna do it this time on momentum. And compared to the mass balance, this momentum balance shows you why it's important to start back here with the integral. So for momentum, what is B? What's capital B?
Be momentum.
Okay, that's momentum, which is, how do we express
Mass times
momentum?
velocity.
Yes, mass times velocity, like that. So what's little b?
Velocity.
Velocity. What's dB dt?
The acceleration?
Not the acceleration exactly. Okay, remember
Wouldn't
we
it be
said
the force?
force. Change in momentum equal to a net force.
And that's because it would be the mass times the acceleration, right? Because mass is constant, so you have m times dv dt.
Yep. So what happens for incompressible flow in a fixed control volume? So what does fixed control volume mean?
The control volume itself isn't moving.
The control volume, well, it could be moving, but it's not changing shape. It's steady state. So this, let's say that's steady state. That's probably, okay. So if we're set steady state, so the control volume isn't changing or deforming, we're not getting any mass built up. So it's not like the situations we did on your homework last time. What happens to that equation?
Does that make d dt 0?
Yeah, d dt of all this stuff is 0.
Question, Dr.
Yes.
Nickerson. With the Reynolds transport theorem, one of these terms is accumulation, right? The one on the left?
Yep. No, not the one on the left. Remember, this is generation / consumption.
Oh, it's the second term, right?
Second term is accumulation. So that's the one that we're saying is 0 in a steady state.
So in a non-steady state, there is such thing as accumulation of momentum.
There is, right? Because the momentum is mass times velocity. So if more mass is building up, then that's going to change your momentum. Sort of like, think of it, you're in a car, and if you throw like a really heavy weight out of the car, the momentum of the car changes. That would be an example of momentum negatively accumulating, I guess.
But if like but if all of it is like moving at the same, like wouldn't velocity be?
Oh, so in that case, it depends on how you define your control volume here, right? So remember, this is all about some control volume, right? So in the case I just talked about with the car, you throw the mass out of control volume, and then of course you have to, it could get complicated because then you have to deal with the other parts. You have to talk about how things are moving over the surface of the system or how the forces are affecting this. But remember, we have some sort of control volume we've defined and mass, and therefore momentum could be leaving it.
Okay, thanks.
Okay. All right. In other words, so a net force is going to equal rho times v squared dA, and I got rid of that normal vector just for simplicity when we look at this, but remember this is going to be v out and v in. It's just the velocity going in and out here.
Is that the velocity going in and out of the system or going in and out of the control volume?
Of the control volume.
Okay.
Okay. However, there is a complication here. And that complication is that we'd like to get out of this integral and go over there. So rho v squared dA does not equal rho v squared AC. So you can't just integrate dA over A, like the cross-sectional area, and turn that into v squared AC. The reason why is because we have velocity profiles, right? Ooh. V is a function of R if this was a pipe, for example. So the velocity is going to be changing over that area. So that means we might end up with more complicated integrals here. People should remember a similar problem that we talked about way back when, or at least some of you will remember this. I don't know how many of you, but some of you will. Does anyone remember a similar problem that we talked about when we were integrating velocity over an area in the past?
This is the reason why we use the kinetic energy correction factor.
Yes, yes, exactly, Zach. That's where that kinetic energy correction factor alpha comes from, right? Kinetic energy correction factor, which we usually assume is 1, so we forget about it sometimes, but it's there. That comes in because kinetic energy is v squared, and so we're integrating v squared over an area, and can make the integration more complicated depending on how velocity changes. Something similar is happening here. And so we define a momentum flux correction factor, beta. Now which is defined like this. I'm going to actually encourage you to look over the example 6.1 in your book. We're not going to do it in class, but I would encourage you to look over that because it shows you how you would find the momentum flux correction factor if you know the velocity profile. It does that for laminar pipe flow. So for a free stream, like let's say out of a hose. So let's say you got a hose. This is my drawing of a hose, and there's just a free stream coming out of it. It's a free stream equal to the air, which means that velocity will be constant across the stream. So the velocity isn't changing there. In that case, beta will be 1. For laminar flow in a round pipe, and as I said, example 6.1 in your book shows you how this is done, and I encourage you to look at it. Beta is equal to 4/3. And for turbulent flow in a round pipe, beta is about 1.01 to 1.04, which again means a lot of times we'll probably assume it's 1, but sometimes also I will tell you taking the momentum flux correction factor to be whatever. It'll be like 1.03 or something. All right, so let's talk about inlet outlet momentum. So in this case, we're just going to, now look at this. Beta rho V average, we're using V average now. So for example, if it's some sort of pipe, we're using average velocity. So that would be the average times, right? That's what we're talking about. So I've split it up. So we have density times V average times the cross-sectional area. What is that if you multiply all those things together?
That's mass flow rate.
That is mass flow rate, Avon. You are right. So this gives us the momentum of an exiting or entering stream. And that means that a steady state momentum balance turns into this.
I have a quick question.
Yes.
How did the control surface area change to the cross-sectional area and the integral?
Okay, so let's say, so I was using cross-sectional area, which perhaps I should have taken a second to explain that I made a kind of a little leap. So let's say we're talking about a pipe and it's like this. So our control volume is just around, it's around the pipe like so. I'm going to put it around the outside of the pipe there so that all of the friction forces are going on inside of it so I don't have to worry about them. That's my control volume. Okay. And so it goes in here and out here. And so the part of the control surface where stuff is going in and out is just the cross-sectional area right there and right there. So I probably should have explained that little leap when I made it, but.
So why don't you multiply it by 2 then if it's like on both sides?
Well, because I was just talking about, well, because the velocity could be, we're keeping this general, right? It's the way you account for both sides is because you do in and out, right? I was just doing it for any generic stream when I did this. Okay, the way you account for both sides of that pipe is going to have some going out and some going in, like so. And there could be multiple ones too. You could have a tank with a hole in it. Yes, Ryan.
So I'm just trying to understand if the sum of the forces out minus in would be negative. Does that mean there's a loss of momentum? And then if it's positive, it's gaining?
Okay. So a loss in momentum, when we're talking, so force is a vector, velocity is a vector, acceleration is a vector, momentum is a vector. So when we're talking about momentum as a vector, does negative mean there's less of it? Or what does negative mean?
It's just in a different direction now.
In a different direction.
Okay.
So, Okay. Everyone's written this down. We're going to do some examples. That's what we're going to do through the rest of class. Your book, there's lots of different sort of interesting problem setups you could do with these momentum balances, which is why your book has several examples. Example 6.2 through 6.7 in your book. So that's 5 different examples of different kinds of situations where you could do a momentum balance. We're going to go through some of them now. We may skip some of the calculation steps because I want to go through, I believe I have 3 in here and I want to go through all 3. I encourage you to work through all the book examples for yourself. Show all the different things. So we're going to start. We have an elbow here. So pipe, it's flowing through, it's living its life. This is a reducing elbow, which means that it starts wide and it gets smaller, which what is that going to do to the velocity?
Increase?
It's going to increase the velocity. It discharges into the atmosphere. As you can see, we've drawn a control volume, the red dotted lines around the outside of the pipe elbow around there, which is convenient because it means all of the friction forces and viscous forces are going on inside of it, and we can just ignore it when we're talking about the net force on this control volume.
I have a quick question. So when it says 30 degrees Celsius, is that just supposed to be 30 degrees?
30 degrees Celsius, my version just says 30 degrees. The version that is on. Okay. My slides that I believe I'm showing you right now just say 30 degrees.
It's in the problem
The
statement.
problem statement, not the picture.
Oh, okay. Sorry. It should just be 30 degrees. That is a typo that comes from seeing degrees and automatically putting Celsius. There we go. There we go. All right. A gauge at the elbow inlet gives a gauge pressure of 200.2 kilopascals. If I didn't tell you what the gauge says right there, you could have actually figured it out using Bernoulli's law and assuming minimal losses over this elbow. Okay, I give you the cross-sectional area at the elbow and the outlet. Taking beta is equal to 1.03. And the weight of the elbow and the water in it is 5 newtons. And I want to determine the anchoring force needed to hold the elbow in place. So this is a physics problem with forces. What are you going to do first?
I would probably define like the axes.
Probably define the axes, and which it helps to do that, to draw a little picture, draw the forces on it. So that's what I did. So I know that the net force on this guy is equal to that, right? And so because this is direction here changes, I'm going to split this into an X direction and a Y direction. What forces are going to be acting on this on this elbow in the X direction?
Would that be the force of the water?
The force of the water, so that is what we're going to find in the end. Well, actually, yes. Or we're actually talking now about the forces of the bend on the water, is because we're doing the balance on this control volume here. And so this is going to be the forces that the bend right there is exerting on the water.
You can't see what you're, oh, there it is.
Okay. All right, in the Y direction, we have the weight of this acting down. And then we're going to call this force R for force reaction. So there's a reaction force, and this comes from the bend as it's attached to whatever it's attached to. Let's say there's a screw right there. Okay. So we call that force reaction. There is another force on here. We've got the weight, we've got the reaction force.
Friction?
There is friction, but friction's happening on the inside of the pipe. We've drawn our control volume around. It's not going to create a net force on this. But something else will.
A pressure force?
The pressure force. Okay, so there's also a pressure force, which I would probably draw right there. Force, pressure. Now, pressure is also pointing in right here. That's atmospheric pressure. I am going to ignore all of the forces that caused by atmospheric pressure because the atmosphere is acting everywhere here. Like the atmosphere, the atmosphere, the atmosphere. It's going to cancel out. So the atmospheric pressure is acting everywhere on this volume. So it's going to cancel out. And instead, there's going to be a force pressure there, which that would be, how would you define that?
Would be that force times the area, right?
Yes, that force. Well, that pressure you mean. It's going to be the gauge pressure times that area. Call it area 1. So it is the gauge pressure because, as I said, I'm canceling out P atmosphere everywhere. The force that comes from pre-atmosphere just cancels out everywhere. We end up with the gauge pressure times the area. Okay, so now I'm going to set up two balances. one in the X direction and one in the Y direction. So in the X direction, we have F reaction X plus F pressure, I'll call it F pressure 1 because it's at point 1. And this is going to equal the change in the momentum in the X direction. So that means, here I'm going to write this more clearly. Okay.
Wait, Dr. Eckerson?
Yes.
Are the purple arrows the forces on the pipe itself or on the water?
Is on the whole thing. It's on the control volume I drew, aren't there, right? But
Ooh, okay.
okay. Mm-hmm.
So would those arrows, like, would the direction actually end up being the opposite way for force Rx, or did you just draw it generically?
Okay.
And it just end up
So
being-
this is what we'll see. I'm just going to put FRX as positive here when I write it out. And positive would mean pointing in the right direction, towards the right. But you have already noticed that the water actually sort of changes towards the left, which would be the negative direction. So when we solve this, what is going to happen is that FRX is going to come out to be a negative number. So if I wrote it down as positive here, meaning it's pointing to the right, and when I solve for it, I get a negative number, that means it's pointing to the left. Okay. Force, pressure, 1. So that's going to be the change in the momentum in the outward direction. So that's going to be m dot v out x minus m dot v in x.
So what do you mean when you say reaction force? Is that like
The reaction force is so the momentum of this water is changing through here, okay?
Mhm.
So there's a reaction force from that momentum change that comes from where it would act. It comes from this pipe's getting held in place. So this pipe is getting held in place. It's not moving, even though there's this momentum change going through it. And so you
Okay.
hold that in place, and we call that the reaction force.
So if there was no anchoring force or if there was no anchor, there would be no reaction forces, and then it would just move with the
It would just
fluid?
move like a rocket. There's an example with a rocket, with a spaceship actually, which hopefully we're going to get to. If we're not, you should look at it in the book. But in this case, this is the force that it takes to hold it in place. You hold it still, you get this force. That's reaction force.
Okay.
Okay.
Thank you.
All right, and I'm going to put in P1 gauge times
Hey, Dr.
K1.
Nickerson.
Yes,
At the end of all this, would you mind posting this recording to Learn this week?
I will. Just
Thank you so much.
all right. In fact, I'm going to make extra sure I am recording right now. I am recording right now. Good. Good. Wonderful. All righty. So that's that. Now, mv out x. So the velocity out is right here. That's the velocity out. As you can see, it's kind of going at an angle. So it has an x component and a y component. What is the x component of that velocity? I'm just going to call it v2 I want the x component there. What's that going to be?
Don't you just multiply V2 by cosine of 30?
Cosine 30, cosine of the angle. Yes. Exactly. We did this earlier in the class, and also you did it in your physics classes, split things into x and y directions. We know how to do it. We're good. All right. And then minus m dot n, call it m dot 1, times, and just m1, velocity 1 is all in the x direction, so I'm just going to call that v1. What if the velocity n was going into the left side instead of going right? What would I do then?
You would have to flip the sign.
Rankin, what did you say? Is that you?
You would have to flip the sign.
You'd have to flip the sign. So if the velocity n was going left instead of right, then I would have to put it in as negative velocity 1, like that. In this case, it is not doing that. So,
Also, don't we have a beta on the right side?
oh yeah, forgot about the beta. Beta is in all of these. We said it was 1.06, I think.
03.
1.03, okay.
I just have a quick question with the force of the pressure coming on point 2. So
Uh-huh.
did we say that that one is ignored because we took that into account? Or I guess could you just explain again why that one is not in our force balance?
Pressure on 2 is P atmosphere. The atmospheric pressure is acting literally everywhere, all over this volume. And so it cancels out. So all the force from atmospheric pressure cancels out.
Okay, so if that weren't P atmosphere, if we were emptying into a pressurized tank or something, would we then have to include that as the gauge pressure at point 2 and include that in our force
Yeah,
balance?
so if for example, it was P atmosphere out here, but then it opens into some kind of pressurized tank, then yes, you would have to include the pressure from the atmosphere there, which means you'd have to split it into an X and a Y.
Okay, but as it is, then anything that's P atmosphere acting on the outside just ends up canceling out if we assume that it works everywhere. And that's the same reason that we used the gauge pressure at point 1, is because we just kind of took out P atmosphere all around, and whatever is left is just gauge pressure acting on any point. And at point 2, because it's P atmosphere, then gauge pressure is 0.
Yes.
Okay, perfect. That makes more sense. Thank you.
All righty. Okay. And so then you can solve for F reaction X is equal to beta m dot 2 V2 cosine theta minus beta m dot 1 V1 minus P1 gauge A1. And as I said, we're not going to take the time for you to actually calculate that. What it comes out to, you can, this is 6.1 in your book. It comes out to negative 2.053 newtons. So the negative means it is acting in the left direction, which is also what we should just expect if we look at it and think about it. All right, and then for Y, minus W, weight acting down, so something we can do to simplify here. Is there any in velocity in the Y direction?
No.
No. And then V out is gonna be V sine theta V2 sine theta is going up, so it's in the positive direction. And we could solve for this component of the reaction force. So basically that's saying that whatever bolt or whatever is holding this elbow in place is got to apply some force in order to hold up the weight of the elbow in the water, and then some force in order to move, in order to hold the bend in place as it's moving the momentum up. Okay. Which, as I said, it becomes 144 newtons. It is positive, so it is in the up direction, just like we would guess it would. And then you can also put them together and get a magnitude at some, acting at some angle. It would be sort of, if X is negative, so means to the left, and Y is positive, meaning down. If you put them together, you could get a magnitude going sort of up and to the left. All right, any questions about this? I do have two more examples here. If you want to and can stay after the official end of class, I will go through them, though I also have faculty meeting. But as I said, they are in your book as well, and I will happily talk to you about them at office hours or other times. You send me text or an email or anything like that. Any other questions about this example?
I have one question, Dr. Nickerson. So we can kind of, so like thinking about this problem, if the water is like pushing out and up like that, like intuitively, I would like think that the reaction force in the X direction would be pointing to the left already, but you can kind of assign it arbitrarily and then the sign will like
yes,
determine what direction it is, right?
That is what I was saying, yes. So
Yeah.
if because of your intuition, you decided to put it in as a negative when you put it into the equation, and it came out and you solved and got a positive number, that would mean, yes, it is to the left.
Okay.
All right. You could do that. There's nothing stopping you. This, if you do it like this and you just always make it positive, then that just it might be easier to keep it straight. Because if you always put it into your balance equation like this as a positive, then if it comes out as a positive, it's pointing to the right, however you define the positive direction. And if it comes out negative, it's pointing in the opposite.
Okay, great.
So with the mass flow rates having slightly different notations, are we assuming they're not the same? And so this is non-steady state?
Actually, no. In this case, if this is incompressible, which it should be, then m.1 should equal to m.2. I just went through and added the little 2 just to be scrupulously correct, because there could be, if this was an incompressible, let's say it was like this. Instead of an elbow, let's say, but so in this case, m.1 and m.2 are the same actually, but, and so you could just call it m dot and that would be fine. Nothing wrong with that. But let's say like it comes in like this, and here's a box, and then it goes out like this and like this. And let's call that 1, 2, and 3. In that case, m.1 would equal m.2 plus m.3, and you'd have to figure out what m2 and m3 are. But
okay, thank you.
Okay. Right.
So I had a quick question. So how would you calculate the weight in this case? Would it just be m dot times gravity, or?
It wouldn't be m dot times gravity. We were told here, because the dot does not really, the rate does not tell you how much, it's just how much water is in here at a given time. And that actually does not depend on the rate that the water is going through, right? Like, let's say that the volume inside of here is 1 meter cubed. That's the volume inside of this elbow. Then the amount of water that's in there at any instant is going to be, rho times. Going to be about 1,000 kilograms. So that's what we meant by the water. So it's the weight of the elbow itself, made of metal or plastic or whatever, and of the water inside of it. And the water inside of it is just determined by the volume, actually. It's incompressible. So you would have to, yeah, so the weight is just gonna depend on what the weight of it is. You'd have to measure it or be given it or know the volume inside there or some combination of that. A lot of times you can assume the weight is negligible. Okay. Now, all right, and that is sort of the basic thing. And if you follow these steps, split it up into X and Y, set up your force balance, solve for it, you will be able to do any problem like this. And so I'm glad we were able to go through it in class because it's probably going to be our most common problem. But I do want to briefly go through a couple other examples that have a different setup, and we'll just sort of go through the setup. Ian?
Yeah, so do we like always just draw that resultant force, or only if we're trying to figure out the reaction force, only if we're trying to figure out how much force we need to keep it there?
Well, that reaction force is always going to be on there, right? That's just an example of one reason we might want to know what that force is because that is the force required to keep it there.
So is that reaction force coming from whatever you're using to hold it down? Or you said it had something
That's how it would physically go on. The place it would probably actually act would be like the screws holding it in, probably.
Okay, is it coming from the water itself, or?
The reaction force is the force that's acting on the water and the elbow. It's acting on that entire control volume that I drew that went around the volume and the elbow. That is the reaction force we're calculating there. Yeah.
Okay. And also, could you like post the homework, or I guess you could do that after you go through these, but.
All right, sorry about that. Yeah, the homework will be posted very soon.
All right, thanks.
Yeah.
Dr. Nickerson?
Faculty meeting, but I'll try to get it up by 1. Okay, I do want to go through these examples because it's a little bit different. So this one, we have water coming from a nozzle. Boom, it goes out. I'm going to make it blue. It hits a cart like this that's moving horizontally at 10 meters per second in that direction. Okay, it's coming out of the nozzle at 35 meters per second. Because this is just a free stream coming out here, what does that mean about beta, kinetic energy correction factor?
It's 1.
Okay. This equals 1. And we want to know how much force has to be applied by the by the brakes of this cart to keep it from accelerating. Okay. Alrighty. Now the reason I wanted to go over this example is because let's draw the forces. So the water hits like this. And when it hits like this, we say it's gonna go up, then splatters in all different directions. Okay, we're going to draw our control volume sort of around it like so. So there's a couple reasons I wanted to go over this. And one is So first of all, it's just atmosphere. There's P atmosphere everywhere, so there's not going to be any pressure forces on here. So the sum of the forces in the x direction will just be what I'm calling F reacts so the force acting on the water here, what direction do we think it's going to act?
To the left.
To the left. We think it's going to act to the left. The force that the cart's surface, the cart's brakes have to apply to keep it from accelerating, what direction do we think it should be acting?
All right.
Will it? If the brakes of the cart act to the right, that's going to push the cart to the right, right? This water is pushing the cart to the right.
So it's just going to go opposite.
Yes, the brakes should apply a force in the left direction. So this shows us how what we're calling the reaction force from, in this case, the cart, is going to act in the left, and also the force that's going on the water is going to act in the left. Okay, so hopefully that should intuitively show.
What do you mean by the force that's acting on the water?
Oh, well, because the water goes to the right. And then it's not going to the right anymore. It's going up and down.
Okay.
And I guess in and out like that.
With brakes, doesn't
this way.
Oh,
sorry.
No, sorry. Go ahead. Finish.
Okay. Yeah. So the water goes from going this way to the right to not going that way, from going up and down. Okay. So the force acting on the water has to go to the left, and also the force of the brakes on this cart have to go on the left because the water is going to be pushing it to the right. And so we should see what I mean when I say that what I'm calling the reaction force here is going to be the same as the force on the water. Okay. Hopefully
So
that's intuitive with this example.
So when I was thinking of brakes, I mean, there's some kind of like force acting like downward, isn't there?
Yes, but it will act down and like it'll put something on the ground, which will create a friction, something. But on net, there has to be a force acting that way to the left. So maybe could call it the force that needs to be applied by the brakes of the cart to prevent it from accelerating. That's what the brakes would be doing, is that they would be applying a net force to the left. It has to, because the acceleration would be happening in the x direction. So the brakes might physically do that by like pushing down on the ground, but what they're ultimately doing is applying a force to the left.
Gotcha.
Okay. All right. Force reaction X is equal to beta m dot V X out minus beta m dot V X in. So is there any velocity out in the x direction? No. Now, another reason I wanted to show you this is because the velocity we should use here should be the relative velocity with the cart. Call it VR for relative. In this case would be 35 meters per second minus 10 meters per second, 25 meters per second. This is the velocity of this fluid relative to the cart. Everyone understand how relative velocities work? Okay, that's why another reason I wanted to talk about this example, because we have a relative velocity going on. And then,
why is Vx in? Why is that 0? Because it's coming in at 35 meters per second.
oh, sorry. It's Vx out, that's 0. Sorry about that. So it's Vx out, that is 0, and it's Vx in, that is this. All right, and so then you'll notice that that says force Rx is equal to negative beta m dot V in, or what I'm calling VRN. Okay, and so if n is positive 35, this is going to be negative, which means that this force is acting in the left direction, just like we said. Then what about the y force, by the way?
Wait, Dr. Nickerson, so I had a question about the orientation in the x-plane. So if fr of x is positive, then aren't we saying left is positive? So then
Well,
wouldn't...
I'm saying that right is positive. No, right is defined as positive, right? And so when I put in this equation, I just put in frx as positive right there, which would mean that it is pointing to the right. But then when I solve the problem, I get a negative number, okay, because frx is going to be equal to negative beta v. And so the negative number I get means frx is pointing to the left.
Okay.
Okay.
Okay, I got it, thanks.
All right. And then let's talk about in the y direction. Y
you
or
just
the
quickly
direction,
explain the
every
writing
direction
in
other than
green?
x. This water splashes out in all directions, so it cancels out. So if there was just a y direction going on, and we would get half of the water will go up, half of the water will go down, it will cancel out. So in every direction other than x, the net force will be 0. Because some of it's going to go up, some of it's going to go down, cancels out. The same amount is going to go up and down, it'll cancel out. Okay, that's why I wanted to talk about this problem. It's got relative velocity in it. It has got, okay, as I said, you should get a negative value. Again, going from the book, I believe it comes out to negative 536 newtons. It's negative, it is acting in the left direction. Again, I repeat, this should show us how the force on the water is negative and the reaction force that's coming from, in this case, the cart, that way. Okay, I see your faces, see you kind of nodding. I want us to get to a point where this is intuitive. Questions that we have. Okay. Now, so the last example that I wanted to give to y'all was flow with no external forces. So for example, let's say a rocket in space. And we have an example problem. Again, this is in your book, go through it. It has good detail about this rocket. And it spews some of its fuel, spews it down in order to slow itself. Okay. So what it's doing, so the fuel is solid inside the spaceship, and then it explodes it, it turns into super hot gas and it spews it down. So if the momentum and the y direction, if we were to write a little control volume around here, and it's coming out like this. So the momentum change in the y direction changes from 0 to negative 3,000 meters per second, because it's gonna spew downward. Okay, and so what that would mean, okay. And so the velocity coming out is 3,000, it's pointed down. So that should be negative 3,000.
And on that one, will we have to change that from the negative 3,000 to the negative 2,200 so that it's relative
so
to the spacecraft?
The problem says 3,000 relative to the spacecraft. So in that problem, it's already done. Okay.
Oh, okay.
As I said, I do have to go to the meeting now. We always end up going through the examples slower than I think, but do go through them in their book and come and talk to me about them. All right. See you all soon.
Thank you.